as I was saying, we're going to talk briefly, and I can spend a lot of time about it, about the law of parsimony. The law of parsimony, okay? And to teach you about that, I'm going to read you the story of Clever Hans. It says, not all explanations for a knowledge claim are created equal. Some explanations involve more details and make more assumptions than others. Assume that you are confronted by two explanations for the same phenomenon. Both explanations seem equally plausible. Which one would you select? The one that involved numerous assumptions and details, or the one that involved fewer assumptions and details? What do you think? Gage? You can stop acting like that and try to listen, please. So I'm asking you, Gage, which one would you select? The first one or the second one? Why is that? Just a guess. Good guess. Okay. So those two guesses were one which was lots of details and more assumptions, and the second one was less, right? Okay. So basically, the law of parsimony says if there's two explanations for something, which one is most likely the correct one? The one with lots of crazy details and stuff, or the one that's kind of simple? The simple one. In fact, the law of parsimony is a fancy word for the KISS principle, which is not the KISS principle, no. Keep it simple. Keep it simple. No double reverses, just run the pitch play, Kish. Okay. So here is an old but excellent example of the law of parsimony. In the early 1900s, Mr. Wilhelm von Osten, a retired mathematics teacher, owned a remarkable horse named Clever Hans. Hans became world famous because he could apparently solve mathematical problems that involved decimals and fractions, tell time, and read, among other remarkable abilities. For example, someone, his trainer as well as strangers, might ask Hans what 7 divided by 4 equals. Hans would tap out the answer with his hoof and receive a treat when he was correct, which was well over 90% of the time. Okay, so they would ask him a question. Usually they would have the guy, see how he's holding the stick there, right? And as the horse tapped his foot, he would go across, and then he would get to the part where the right answer was, and the horse would stop tapping. That's how he would tell him what the answer was. Okay, and then he'd get a treat. And he got like 90% of the questions right. A committee that included the noted German psychologist Karl Stumpf was appointed by the German government to study the phenomenal horse and prove that his so-called abilities were nothing but a hoax. The committee completed their task and reported that although they were unable to prove that Hans was receiving intentional cues, they remained unconvinced that he was able to solve such mathematical problems and complete the remarkable feats by using his cognitive processes. In other words, like he could think it through. Stumpf's assistant, Oskar Funks, decided to continue investigating the phenomenal horse. Funks conducted several experiments and concluded that when Hans could see the person asking the questions, then he was able to supply the correct answer. So in other words, they had a guy stand in front of the horse. I'll ask Matthew to pretend he's the horse right now. Want to make a horse sound? Okay. And he would ask him a question, right? And then the horse would get it right. But then when the guy did this and asked him a question, well, then the horse couldn't see me, and he couldn't get the question right. What's up with that? Okay, well, someone said this morning the horse is lip reading. I don't know about that. Okay, but so if Hans could see the person asking the questions, then his performance fell to near zero levels. Funks was faced with two alternative explanations for the horse's abilities. Either Hans understood the questions and was able to use a cognitive process, but only when he was able to see the questioner to solve the problems. In other words, his brain only worked when he could see the person asking the question. Does that make any sense? Okay. Or the second one was that the person was asking the question was somehow inadvertently cueing the horse when to stop tapping at the appropriate moment, telling the horse, you've got the right answer, you should stop now. Applying the law of parsimony, Funks chose the latter explanation and persisted in his investigations. He finally determined that almost everyone who asked questions of Hans made a minute upward movement of their head when the correct answer was reached. The horse used this cue to stop tapping and receive his treat. This was an instance of positive reinforcement. So in other words, when the person asking the question, he's got his stick up there, the chart, and when the horse got to the right answer, the guy sort of went like that, eyes got big or whatever, maybe went up on his toes or something like that, and the horse realized that that was a signal for stop, and then he got his treat. So all he really had to know was just keep stomping your foot until the guy goes like this, and then I get a cookie. Pretty smart horse, but could he do fractions? No. If you apply the law of parsimony as you evaluate knowledge claims, you are well on your way to becoming a good psychological consumer. Some additional points to consider as you evaluate knowledge claims are covered in the next section, and we're not going to bother with that. I will tell you another example of the law of parsimony, one that you're all familiar with. Okay? Originally, they thought the Earth was at the center of the solar system, right? And they thought the planets revolved around it, but to make it work, they had to have those little loop-de-loop thingies, right? And some had more than others, and it was all quite complicated. And then along came Copernicus, and he said, that's crazy, there's way too many exceptions, and there's way too many rules for this. If we just simply do what? Put the sun at the center, then what happens? Everything just sort of goes nice. Law of parsimony. The simplest explanation is most likely correct. Okay, does that make sense? Okay, let's stop with that. All right, let's continue on here. So, I'm going to talk to you a little bit more about vector direction. We're going to talk about vector addition here. And eventually we're going to actually do some vector addition. Oh, yeah. I would actually like, I'd like a T-shirt, a supervillain with size, and there's got to be a T-shirt like that, right? It's got to be. So a vector is a quantity which has both magnitude and direction. It is not, however, a evil villain. Examples of vectors include displacement, velocity, acceleration, and force. To fully describe one of these vector quantities, it's necessary to tell both the magnitude and the direction. For instance, if the velocity of an object were said to be 25 meters per second, then the description of the object's velocity is incomplete. The object could be moving 25 meters per second south, north, southeast, or whatever, right? To fully describe the object's velocity, we need magnitude and direction. Now, in order for such descriptions to be useful, it's important. Can I put this away? How do I put that away? Auto hide. There we go. In order for such descriptions of vector quantities to be useful, it's important that everyone agree upon how the direction of an object is described. Most of us are accustomed to the idea that up on a map refers to northward and right on a map refers to eastward direction. How many people have seen the map in Mr. Dick's former classroom and now his office that has the world upside down? Have you seen that map? It's kind of weird to look at, right? Okay, but who says north has to be up? It's the convention that we use. So this is a mere convention which map makers have used for years and upon which we can all agree until someone comes along and decides to change it, right? What if the direction of a vector quantity is not due north or due east, but somewhere in between north and east? For such cases as this, it's important that there be some convention for describing the direction of such a vector. We use the bearing method that has north at 0 with the directions rotating clockwise. Don't do the math thing, right? So there it is there, right? North is 0. Northeast is 45, east is 90, and so on clockwise. Remember, the math people like to start at east and go, start at east and go counterclockwise, okay? But that's a math thing. It's got nothing to do with directions. It's the unit circle, so it's different, okay? Okay, 6 plus 8, 14. Most of us are accustomed to the following form of mathematics where 6 plus 8 is 14, as Connor says. But what if I told you that 6 plus 8 was also equal to 10, to 2, and 5? I am not full of it. When we become students of physics and approach the task of adding vector quantities, we soon become aware of the fact that the addition of two vector quantities with magnitude of 6 and 8 will not necessarily result in an answer of 14. The rules for adding vector quantities are different from the rules for adding two quantities arithmetically. When I say arithmetically, I mean just adding the numbers together. If you're adding vectors, you also have to add the direction, Matthew. You have to add the direction. So 6 plus 8 might be 14, but not necessarily. Vectors are quantities that include a direction. As such, the addition of two or more vectors must take into account that the quantities being added have a directional characteristic. There are a number of methods for carrying out the addition of two or more vectors. The most common method is the head-to-tail method of vector addition. Using such a method, the first vector is drawn to scale in the appropriate direction, and then the second one is drawn that its tail is positioned at the head of the first vector. And we call this head to tail or tip to tail method. And let me just draw. Do you guys have a space there for a picture? Sort of, kind of? No? You can probably figure out a way. Okay, so there's a blue one. There's a red one. Okay, so this method is referred to as, I call it tip to tail. Okay, because you've got vector 1, the tip of vector 1, right up against the tail of vector 2. That's the tip to tail method that I'm talking about. It can be called head to tail as well, right? Is that what you did yesterday with the pirate thing? Yeah. Absolutely. You just didn't put the arrowheads on, right? And I understand sometimes the arrowheads get in the way of the measuring. So if you want to put the arrowheads on after, no problem. Okay? So this would be called like vector 1, and this would be called like vector 2. Now, when you add two numbers like 6 and 8, what's the answer called? Starts with an S. Sum was the one I was looking for. Sum, okay? When you add two vectors together, you get what's called the resultant, and it's right here. The sum of two such vectors is then represented by a third vector, which stretches from the tail of the first to the head of the second, and this third vector is known as the resultant. I'm going to find the highlighter. Resultant. Now, Despicable Me 2 is out in theaters soon, is it not?
Yes. What? Really?
I am going to, and I just realized this morning, clearly there is a science physics nerd on the writing staff. Otherwise, there would not have been a villain named Vector who has both size and magnitude. I'm going to wager that he or someone else becomes the villain resultant, the sum of two vectors. You think so in Despicable 2? Just in case? If that happens, you'll all think of me, right? Resultant, because he's more powerful than two vectors combined. Yeah, I know you were. Yeah. I haven't watched the trailer, no. Maybe, we'll see. Okay, so the resultant is the vector sum of the two individual vectors. Of course, the actual magnitude and the direction of the resultant is dependent upon the direction in which the two individual vectors have. Now, what I'm talking about is this. If I add those two vectors, but if one of them is changed, like what if vector 2, let me just take a second here. And let me just do this. I'm going to copy this one. You don't have to draw this. I'm going to put the blue one there. I'm going to take the red one. I'm going to copy it. Okay. But I'm going to change, I'm going to change the direction. Change the direction of the vector a little bit more. Okay, and now I'm going to place them tip to tail. Now, do you think if I take this resultant right here, paste it over there, there's a black one. Now, if I put that there and I rotate it, is that going to be the same? Should it be? No, it shouldn't be. It might coincidentally end up being the same length, but clearly you can see it's not even close, is it? Right? How come here, if these are 6 and 8, how come here 6 and 8 equal that length, but here 6 and 8 equal another length? Because you have to add the direction as well. Okay? How are we going to do all that? With a ruler and a protractor. Okay? With a ruler and a protractor. What else we got here? Oh yeah, here it is here. The principle of head-to-tail addition of vectors is illustrated in the animation below, which I'm going to have to go and find for you. In each frame of the animation, a vector with a magnitude of 6 in green is added to a vector with a magnitude of 8 in blue. The resultant is depicted by a black vector, which stretches from the tail of the first to the head of the second. Let me just go find that little animation. No, I don't think you have. So you can see here, you'll see the green arrow changes the direction. When it's, I'm just going to start again here. When it's pointing to the right, how long is the resultant? 14, 6 plus 8, right? But when it's pointing back the other way, how long is the resultant? It was 2. So the actual resultant can be anywhere from 2 all the way to 14, right? 2 when it's exactly opposite, 14 when it's exactly in the same direction. What's the one mistake with the directions up there? Have a look. What one thing is wrong? The blue and the green are tip to tail. Yeah, it starts. They're saying that 360 or 0 is east. They're doing it the mathematical way, right? Silly math people. Okay. So yeah. Good. All right. Now you know what I ended up doing this morning was I ended up just ignoring the rest of this thing here.
Awesome.
What about, we already know about the order, right? Does the order matter? The order that you add them together? Like, let me show you this. Let me show you this here. I'm just going to, where are my vectors? Let me grab these three again here. You go away. Let me grab those guys again. Copy those. Let's go a brand new one here. There we go. Okay, so here I've got them all, right? What if I don't go blue and then red? What if I add red and then blue? Should it be the same?
Yeah.
How am I going to know? Does the order of the vectors matter? No. And yet, I say that over and over again, and yet there will be one question where someone will put their hand up, they'll call me over and they'll say, Mr. Bennett, does it matter what order I put them in? They will. Don't let it be you. Don't let it be you. Okay, let's talk about vector addition. What I'm going to do is I'm just going to work through these with you to give you sort of an understanding of how to do them, okay?
Okay.
No, I'll do the first one for you, okay? A car is driven 125 kilometers due west and then 65 kilometers due south. What is the displacement? So they're asking you for displacement. They're asking for the vector sum of these. So we've got 125 kilometers due west, and then we've got 65 kilometers due south. Okay? You should arrange them tip to tail. Okay? You should arrange them tip to tail. Now, are these vectors set up perpendicular to one another? They're 90 degrees, right? West and south, right? Okay, so west and south. Now my resultant then, now I didn't talk to you about this. The resultant is always from where to where? Okay. It's not tip to tail. It's tail of the first one to the tip of the second one, okay? Occasionally I get kids that want to do this, okay? They want to do this. They want to complete the circle. Okay, and they say, well, that's tip to tail. If I walked 125 west and then 65 south, where would I be? I would be, how far am I from the start? I'm that direction. I could also go like that, right? If you draw it like this, then you don't have a displacement, okay? So people worry about this. They go, but if I go like that, then it's not tip to tail. It's not supposed to be. What's supposed to be tip to tail? The two that you're adding together, okay? The resultant is always from where you start to where you end. Okay, it's always from where you start to where you end. Okay, so that's the result. Now it's Pythagorean theorem. Okay, how come? Because it's a 90-degree triangle, right? So now I'm going to write r squared is equal to 125 squared plus 65 squared. Okay, and then you can work that out. That's what it is. A, B, R. It can be R or R. It should be R. It's the resultant. It would be like me calling you a different name. Oh, sure it is, Tabby. R is 140.9. And that would be kilometers. Am I done the question? No, I need to do what? I need to do, remember, because vector, the villain, has both size and a direction. Oh, yeah. Oh, direction and magnitude? Magnitude and direction, I think. Now, which, I did say that, didn't I? What angle am I actually talking about here? No, but where in the triangle? This one? And I get kids asking me this question too. They want to know which angle to measure. Is it this one or is it this one? It's always from where you start, Tristan. Exactly. It's always the angle from where you start. Okay? Now, this is a right triangle, so we can use our sine, cos, and tan. Remember, SOHCAHTOA, right? Sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. We are talking about opposite and adjacent, right? So we're talking about tan. Do I need the angle or do I need the tangent? I want the actual angle. Okay, so it would be like tan theta is opposite over adjacent, right? So tan theta is 65 over 125. Now, how do you take tan to the other side? Like, how do I get theta by itself? It's the inverse tan. Second function, it's tan minus 1. It's not like minus 1, it's tan to the minus 1. Inverse tan 65 over 125. And you should get out of that. I'm just going to do it. Now, on your calculator, actually, I should talk about this. Some of you will have a reverse calculator, and some of you will have a forward calculator, Tristan. Okay, so some of you are going to have to go 65 divided by 125 equals, and then second function tan. And others are going to be able to go second function tan, 65 divided by 125, and then hit equals. But either way, you should get a value of 27.47 degrees. Okay. Now, navigational people, they do not worry to tenths of a degree, so we're going to round that to plain old 27 degrees. Okay. A tenth of a degree is not that much. Okay. Now, is that now done? Still not, because I need to. No, I need to say which, like, is it east, is it south, what is it, right? So it's going to be east 27 south. That's because it is west, not east. I messed that up, didn't I? Left is. So the answer is, you'd get 1 mark for the 140, 1 mark for the diagram there, and 1 mark for the actual angle. Quite a few, yeah. I'm a big believer in giving out answers. Really? No? You got to learn from them. Now, without looking at the back, how about you guys try number 2? I said without looking at the back there. Despicable Ben.